Right. So last class we discussed Biot-Savart law. Okay. The magnetic field, the small magnetic field dB produced by a current element IDL. Then we discussed applications of Biot-Savart law to calculate the net magnetic field produced by a circular current at its center, then arc at its center, and a straight current carrying wire at a finite distance x from it. Okay, we'll work on this formula today. Notice the final result that we derived. We got B, that is a magnetic field produced by the current carrying wire. Okay, straight current carrying wire is mu naught I by 4 pi x. I is the current in the wire. The current I has to be same everywhere in the wire. Okay, usually it will be, but just in some cases they may twist the question. They may ask you, or they may say another wire, a junction is there here. They may say current in this is I1, in this the current is I2, then in this part the current will be I1 plus I2, right? Basic KCL. Okay, then you will have to use some other techniques. Okay, you'll have to split the wire into two parts and find out magnetic field produced by each part separately. Not a big deal, but we'll work on this formula today. So I is the uniform current in the wire. X is the perpendicular distance from the wire, as you can see in the diagram. And what are theta 1 and theta 2? This is the most important thing. Let's draw it here itself. Just a moment. So suppose this is the straight wire whose magnetic field you want to calculate. And assume this is the point where you are required to calculate the magnetic field. Okay, let's call the point as P. This perpendicular distance is X. Okay. In the formula, we have theta 1 and theta 2. So remember what theta 1 and theta 2 are. When you connect the point P to the ends of the wire, like this and like this, the angle subtended by those connecting lines with the wire are theta 1 and theta 2. Fine. Now, sometimes the situation may not always be like this. No, sometimes it could be like this. Let's say this is the wire, and the point where you are required to calculate the magnetic field is somewhere here. You imagine connecting that point to the ends of the wire. These are the lines which connected to the ends of the wire. Then the angles will be, this one you should take as theta 1. This should be taken as theta 2. The internal angle should be taken as theta 2. Theta 1, theta 2, both are internal angles. Okay. Another case. Let's say this is the wire and you are asked to calculate the magnetic field at this point. Again, imagine connecting the point to the ends of the wire. You will have to take this angle and this angle. Not the, I mean, here you can see, you should not consider this angle. That will be considered as an external angle to this triangle. You have to take the internal angles, right? Because the derivation is based on that. Right. So first, let us extend that result. We know that magnetic field produced by a finite wire, finite straight wire carrying a current I at a distance x from it is mu naught I by 4 pi x cos theta 1 plus cos theta 2. Okay. We'll extend this to an infinite wire. So if any of you can tell me, you tell. If the length of this wire extends to infinity, what will theta 1 and theta 2 tend to become?
They both will tend to become 1. So everything will be like the cos theta 1 plus theta 2 will be 2.
Okay, angles will tend to become 0. Fine. And the whole thing will become 2. Correct. See, if you imagine extending the length of this wire, okay, say it is this much. Now you connect the point P to that end of the wire. You will see that the connecting line subtends a smaller angle now. Here it was theta 1. maybe some 60 degrees or 45 degrees. Here it is much lesser, maybe 30 degrees. Okay, so as the wire becomes longer and longer, those angles theta 1 and theta 2, they become smaller and smaller. So if the wire is of infinite length, okay, theta 1 and theta 2 both tend to become 0, and cos 0 is 1. 1 plus 1 becomes 2. Therefore, magnetic field due to an infinite straight wire, if this becomes 2, 2 and 4 cancel, you will get mu naught I by 2 pi x. Okay, so at a distance x from the wire, it is mu naught I by 2 pi x. Now this gives the magnitude, that's fine. Magnetic field is a vector quantity. We should find out the direction as well. For direction, you can use by like right hand thumb rule. So in this case itself, let's assume there's an infinite straight wire like this. Assume the current is directed upwards. Can one of you tell me the direction of magnetic field at this point P produced by this current? It is governed, the direction of magnetic field is governed by Biot-Savart law, I dl cross R. This is what gives the direction of the magnetic field dB. So you have to check that. Okay, I got one answer as into the screen. That is correct only. Now we discussed two versions of the right hand thumb rule. We'll use the simpler version where you'll have to place your thumb along the current and make your fingers point towards the position where you want the magnetic field. Okay, so if you do that, you will be placing your right hand effectively like this. This will be your thumb and the fingers will be pointed this way. If you do that, your palm will be facing into the screen. Okay, it will be facing towards the screen. So it means the magnetic field at this point is directed inwards. Okay, that mu naught I by 2 pi x, whatever is there, is directed into the screen. Okay. Now consider a point on the left side of the wire. Say somewhere here. Let's call this point as Q. If you want to find out the magnetic field at that direction of magnetic field at that point, what can you do? Again, same thing, you can use the right hand. Place your thumb along the current and point your fingers towards Q. In that case, your right hand will be placed like this. Right? Now, if you see, like if you place your right hand like this, you will see that the palm is facing towards you, not towards the screen this time. The palm is open towards you. That means the magnetic field is directed out of the screen. Out of the screen is indicated with a dot in a circle. Okay. On the right side of the wire, because the current is flowing upward, field is inwards. On the left side, it is outwards. Similarly, you can imagine magnetic field at other points around this wire also. And we have discussed something called electric field lines, right? Can one of you tell me what electric field lines represent? What do they help us, or what do they tell us about the electric field?
Magnitude and direction of the net electric field.
Okay, correct. Good that you used the word net also. Electric field lines indicate the strength and the direction of the net electric field. Correct. Similarly, you can draw something called magnetic field lines, which show the direction of magnetic field at each point. Okay. And also the strength. How do electric field lines indicate strength? Like just by looking at the field pattern, how can you comment on the strength of the field? Anyone?
Sir, if there are more lines, it is crowded, and if there are less lines, it is not. It has less strength.
Okay, if the lines are crowded, the field is strong. If the lines are far away from each other, the field is weak. If they are uniformly spaced, the field is uniform. Correct. The same property holds for magnetic field lines as well. Okay. Now see, on the right side, you observe that the magnetic field at point P, it is into the screen, and at point Q, it is out of the screen. If you get the magnetic field at different points, you will see that you get a magnetic field line like this. It will be shaped like a circle. Just a moment. around the wire. Now, some part of the magnetic field, some part of this field line is behind the screen. The part behind the screen, I'll show it in dotted lines. Right? At Q, the field is pointed towards you. At P, the field is pointed away from you into the screen. So you can even put an arrow like this. This is the direction of the magnetic field around the wire. Okay. Can one of you quickly tell me some more properties of electric field lines?
So they never form a closed loop.
Electric field lines never form closed loop. Where do they originate from?
Like from the positive charge and it goes to the negative charge.
Electric field lines originate from positive charge and terminate at the negative charge. Correct. They never form closed loops. That's correct. Now here, if you see the field line that I have drawn here is a circle. It's a closed loop only. Okay. This is the difference between an electric field and a magnetic field line. Magnetic field lines always form closed loops. Okay. There's no exception. This is the only thing in which magnetic field lines vary from electric field lines. And as a result of this, you will find that magnetic field is a non-conservative field. Okay, that we will discuss later in detail. So remember this is very important. Magnetic field lines always form closed loops. There is no particular point of origin and no particular point of termination of these field lines. Okay, so if it's a straight infinite wire like this, it creates circular magnetic field lines which are coaxial or concentric with this wire, you can say. The centers of all those circular magnetic field lines, they fall on this wire. So you can imagine another field line like this. Again, half of it out of the screen and half of it behind the screen. Direction will be like this. You can draw any number of field lines, not an issue. Okay. Fine. Let's solve some questions based on this. If you have any doubts, you can ask. Magnetic field of a straight wire. Okay. And these are some basic cases only you'll find in many books. Let's say there's an equilateral triangle. Okay. It's a wire in the shape of an equilateral triangle. Assume it carries a current I. And the side of the triangle is A. Okay. Calculate or derive the net magnetic field it produces at its centroid. Okay. Do this, all of you. Okay, can any of you tell me how you are trying to derive this?
Principle of superposition.
Principle of superposition. So you are going to find out field due to each side of the triangle and add them up as vectors. Correct? See,
Yes.
right. See, each side of a triangle is a straight wire and it's a straight finite wire. And you know how much is the magnetic field produced by a straight finite wire at some distance from it. Okay. So there are a few things you need to, what do you say, find out first before you start calculating the magnetic field. You first need to know how much is the distance from the wire where you are trying to find out the magnetic field. Okay. So that distance x has to be known and the angles theta 1 and theta 2 have to be known. Okay. So do that first and then substitute in the formula, you'll get the result. I got one answer as 3 mu naught I by 4 pi a. Okay, we'll see. Two pi a. Okay. Isha, how much is the distance x that you have considered? No response. Okay. Anugraha, what about you? How much distance x did you consider?
For the base, it would be 1 by 2 root 3. And for the
So a by 2 root
other
3 you're
two
saying.
sides, oh yes, sir, a by 2 root 3. And for the other two sides,
Hmm.
Once again, I'm calculating.
Why do you have to calculate? It's an equilateral triangle.
So
It will be
using the,
same. It will be same
but
for
it's
all
centroid,
sides.
no, sir.
Huh.
Would it be same?
Whatever is the distance of centroid
Fine,
from
then
one side,
a
it
by
should.
2 root 3.
In an equilateral triangle, all those points, circumcenter, centroid, they are all the same and they are all equidistant from every side. Okay. And Harika, how much are theta 1 and theta 2?
So theta 1 30 degrees and theta 2 will be it'll be 60 degrees.
Okay, let us visualize. See, remember the diagram, all of you, like the diagram that we drew in the derivation. It's this, right? X is the perpendicular distance between the wire and the point where you want the magnetic field. Okay. Now, sometimes you look at the diagram on the right side. Just a moment. Yeah, you look at the second diagram. In this diagram, can any of you tell how to visualize X? This doesn't exactly have anything to do with the question that I have given, but how to consider X in that second diagram? From where to where shall we take it? Okay, what did I just say X was?
Perpendicular distance to that line.
From the line to the point, no? So you will virtually extend this line and take that perpendicular distance. This will be considered as X. Okay, you cannot consider any other distance as X because in the derivation X was the perpendicular distance. So it has to be kept like that. Fine. Okay, Manasa, we are just discussing some applications of the formula that we derived in the last class. Magnetic field due to a straight finite wire. Okay, we extended it to an infinite wire and we got this formula. Anyway, I'll share the recording, you'll be able to see, no problem. So in case the wire doesn't I mean, in case the point P doesn't fall within this range, how you'll take the distance x is, you'll have to imagine the wire to be extended a little bit and then take the perpendicular distance. X should always be perpendicular to the wire, like this. Okay, anyway, so the magnetic field produced by a straight current carrying wire depends on that perpendicular distance x and the internal angles θ1 and θ2. And how are we getting θ1 and θ2? That is important. You have to connect the point P, the point where you want the magnetic field, to the ends of the wire. If you do that in this triangle, equilateral triangle, you are asked to calculate magnetic field produced by this triangular current at the centroid. So from centroid, we'll first draw lines to the ends of each side, because the idea is to find out the magnetic field produced by each side and add them up, because each side is a straight wire. So let's imagine connecting the centroid to the ends of each side. Harika, now you tell me how much are θ1 and θ2?
So both will be 30 degrees.
Both will be 30 degrees. Okay. It's an equilateral triangle. Total angle is 60. So half angle, 30, 30. Right. The next thing we need to find out is the perpendicular distance. Can any of you tell me an idea to find out the perpendicular distance from a side of an equilateral triangle to its centroid?
Tan 30.
You could use tan 30, correct? You can make use of this right angle triangle that you see, because in an equilateral triangle, see, centroid is actually the line, not line, the point of intersection of medians. Okay. In an equilateral triangle, median and altitude are the same. Okay. Altitude is perpendicular drawn from one corner to the other side. No. In an equilateral triangle, medians and altitudes are same. So this angle becomes 90 degrees. In every triangle, it does not happen like that. In equilateral triangle, it definitely happens. Okay. So you can make use of this right angle triangle to calculate that distance. Okay. We know the angle 30 degrees. That's fine. We need to know something more to find out the distance. Let's call this distance as x. That's what we are looking for. We know that this part is a by 2. Obviously, centroid is the point of intersection of medians. Median divides the side in the into two equal parts, right? So that is a by 2. You can use tan 30 degrees. Tan 30 degrees is 1 by root 3. Is opposite x divided by adjacent a by 2. That's all. So you get the distance as a by 2 root 3. And in an equilateral triangle, the distance of the centroid will be the same from all three sides. You don't have to calculate separately. Okay. Let's just visualize one of them for now. Right. We got the distance, we got the angles. We are now in a position to express the magnetic field produced by one side. Okay. So magnetic field produced by one side will be mu naught I by, the formula is 4 pi x cos θ1 plus cos θ2. So in this case, it becomes mu naught I by 4 pi. In place of x, we have a by 2 root 3 cos 30 degrees plus cos 30 degrees. Cos 30 degrees root 3 by 2. Root 3 by 2 only, no? Another root 3 by 2. This whole thing becomes root 3. Okay. And then if you adjust this equation a little bit, this 2 root 3 in the denominator will go to numerator. So mu naught I into 2 root 3 into cos 30 plus cos 30 is another root 3 divided by 4 pi a. 2 and 4, 1, 2 remains. Root 3 into root 3 is 3. The answer for one side, magnetic field produced by one side, is 3 mu naught I by 2 pi a. Okay. Now one of you tell me, based on the direction of current and the position where you are trying to find out the magnetic field, what is the direction of magnetic field at this point? We found out how much magnetic field is created. What is the direction of it?
So it will be inwards.
Inwards. Okay. Same thing. Point your thumb along the current. Make your right hand fingers point towards the position where you want the magnetic field. Then you'll be placing your right hand like this. The fingers will be pointed this way. You'll see that the palm will be facing the screen, okay, towards the screen, away from you. That means the magnetic field is inwards. Right. Now we have two more sides whose magnetic fields we have to calculate. Now they also have the same current I. They are also at the same distance from this point. They'll also have the same angles, 30 degrees and 30 degrees. So distances, currents, angles are all same. So the field strength due to the other sides is also going to be same. So B1, B2, B3 will all have the same strength. Okay, on what basis are we saying? Because they have the same current, they are at the same distance, and when you connect the point to the ends of the wire, it makes the same angles. Okay, so they should be producing the same amount of magnetic field. Now you all tell me this current I at the centroid, in which direction does it produce a magnetic field? If you imagine placing your right hand thumb along the current, it would be like this. And then you have to extend your fingers this way towards the point where you want the magnetic field. So to actually do this, it will be a little difficult. I think you'll have to, okay, I am having to put it like this. Anyway. Yeah, you put your right hand like this, you'll see that the palm is again pressed against the screen. That means the magnetic field is still directed inwards. The magnetic field produced by the third side also will be directed inwards itself. So all three sides produce magnetic field at the centroid in the same direction. And if three vectors are three or any number of vectors, if they are in the same direction, you can simply add their magnitudes. That will be the resultant. Therefore, the net magnetic field at the center or centroid will be 3 times of the field produced by one side. So 3 into 3 mu naught I by 2 pi a becomes 9 mu naught I by 2 pi a. Okay. Fine. Sashank, Anugraha, Yash. Yash, I think you sent answer for one side. Okay. So basically the idea is that the triangle is made up of 3 straight wires, and we know the formula for magnetic field produced by a straight wire. We are making use of it. Okay. You need to be careful. You need to know that you need to first find out the distance x and the angles theta 1, theta 2, then you can apply it. Okay. So same situation, if a square is given, I think you can manage. Next. Suppose there is a situation like this. Let's say there is a wire bent at right angles. It's an infinitely long wire. Okay, this end is at infinity, the other end also extends to infinity. And assume the current is flowing downward like this. So in that other branch, it will be going to the right. Okay, that's the current. And you have to find out. Okay, let's assume this is the x-axis and this is the y-axis. Let's take this as the origin. So you know how the wire is arranged. And you have to find out the magnetic field at this point P. Okay, no need of taking numerical values. Let's say the coordinates are a comma a. Okay, do this all of you. Derive the net magnetic field at that point P. I got one answer as 2 mu naught I by 4 pi a. You can cancel the 2 and 4, no? But I don't think that is the correct answer. Check your solution once. Again, see, there is one wire bent. So you can take it as 2 wires now, 2 straight wires. And you know what all you need to know to calculate the magnetic field produced by a straight wire. Okay, find out those things first. X, theta 1 and theta 2. Okay, I got another answer as 2 plus root 2 times mu naught I by 4 pi a. Okay. Harika, tell me how much is the distance x? Let's take this wire first. Let this be the first wire. Second one. From the first wire, how much is the distance of the point?
Sir, it will be
The perpendicular distance will be a because the x coordinate is a. Okay, so in place of x, you will write a. That's fine. And did you calculate the angles?
A. So
Made
one
when-
will be 45, another will be 0 degrees.
Good. When you connect that point to the lower end of the wire, the angle subtended here would be 45 degrees because its coordinates are a comma a. Okay, it will be on that line y equal to x. The other end is at infinity. So that line will almost be parallel to the wire. They'll meet at infinity. The angle will be 0. So one angle is 45 degrees. The other angle is 0. It doesn't matter which angle you take first. Okay. Because cos theta 1 plus cos theta 2. It doesn't matter if you do cos theta 2 plus cos theta 1 also. So for one wire, these are the values. Harika, what about the second wire? Is the distance from the second wire also equal to x?
Yes.
Sorry, also equal to a. Yeah, it is a because the y coordinate is a. And for the second wire also the angles are the same. This angle 45, at the other end the angle will be 0 because the other end of the wire is at infinity. Okay. So both first wire and second wire, these are the values. Let us now derive the magnetic field based on this. We know the formula mu naught I by 4 pi x cos theta 1 plus cos theta 2. So this becomes mu naught I. They both have the same current. Okay. See, that is an important point. Okay. Sometimes in a hurry, you may overlook that fact that, I mean, you have to check whether the wires have the same current or not. If there is a junction somewhere, they can give you questions like that. Suppose there's a third wire like this. Okay, that current is I, this current is I. Then this becomes 2I. They won't tell you that. Okay, you have to like analyze that on your own. And even if it is like this wire won't produce any magnetic field here because we discussed in the last class. A current element cannot produce a magnetic field along the line on which it lies. Okay, so only these two will be producing. You'll have to find out. You can find out the net magnetic field. Okay, anyway, let us consider this case itself. So mu naught I by 4 pi x. The distance is a in this case. Cos theta 1, cos 45 degrees is 1 by root 2 plus cos theta 2, cos 0 is 1. That is the magnetic field produced by one wire. It's also the magnetic field produced by the second wire. because the distance and angles are the same. But what we need to calculate is the net field. Okay. Magnetic fields are vector quantities. If you want to calculate the net field, you will have to check the angle between the individual fields. Yes, tell me, what is the direction of magnetic field at P produced by the first wire?
It will be towards the viewer, right?
Okay, towards the observer. That means out of the screen. Correct. Okay. Imagine placing your right hand like this. The thumb will be pointed this way, and fingers towards the point. If you put your right hand like this, okay, the only way you can do it is by, like, it's a little difficult to actually place your right hand like that, but you will see that the palm will be open towards you. Okay, your fingernails will be towards the screen. Your palm will be open towards you. Okay, so the magnetic field is outward. Fine. Anugraha, tell me, what is the direction of magnetic field produced by the second wire at point P?
Outwards, sir.
Second wire will also produce outwards itself. Then the net field, you can simply add the individual fields. It will be 2 times of this. So 2 times of mu naught I by 4 pi a, 1 plus 1 by root 2. You can adjust that if you want. It all depends on how they give the options. Okay, right. Okay, so arcs, circles, straight wires, this is how you find out the magnetic field produced by them. And remember that point that I told you a little while ago. In case the point P doesn't lie within this range, okay, like in these two examples that, okay, I'll just drag this down. Okay, in this second case also, the one on the left side, the point P here doesn't fall within this range, within the range of the wire. Then if you have to take the distance x, you will have to consider this perpendicular distance as x. Okay, virtually you have to extend the wire. And angles will be theta 1, theta 2, those inside angles itself. In that case, one of them will be obtuse. Okay. Next, let us do one derivation. Magnetic field on the axis of a circular current loop. Assume this is a loop carrying current. The loop is perpendicular to your screen. So half the loop will be outside the screen and half the loop will be behind. So the part which is behind, I'll show it in dotted line. Okay. And we have to find out the magnetic field that it produces at some point on its axis. So let us visualize the axis first. Okay. Let's say we need to find out the magnetic field produced at this point, which is at a distance x from the center of the ring on the axis. Okay, the ring or loop. Assume the loop carries a current I flowing like this. It could flow the other way also, not an issue. Let's say it is flowing like this. Assume its radius is r. Okay. Can one of you tell me an idea how to start this derivation?
Sir, first we'll calculate the like the direction of the magnetic field.
Direction of which magnetic field?
Due to the coil, like the current loop.
How can you directly tell the direction of magnetic field produced by the entire loop?
Sir, like Due to one small element.
Element by element you'll have to go, no? Okay. So see, generally also when we calculate fields or potentials, there are two ways to begin. You either take the system as a collection of elements, or you use the results that you have already used. Means you have to consider the system as a combination of other systems whose fields you know. Okay, for example, if you remember, when finding out the potential created by a solid sphere or the electric field created by a solid sphere, we take it as a combination of hollow spheres, because by then we already know the result, knew the result for hollow sphere. Okay. In some other cases also we did that. Disk, if you want to find out the electric field produced by a disk or the potential produced by a disk on its axis, we take the disk as a collection of rings, because we already know the result for a ring. Okay, but how do we derive for a ring? Ring is considered a collection of particles or elements. Okay, so same thing here. There are three things we have learned so far about magnetic fields. First is Biot-Savart law. Current element's magnetic field, we know how to find out. Next, we derived the result for magnetic field produced by an arc at its center. But this point now, the point P, is not at the center of the circular loop. So that arc result will not be useful here. And we also know the magnetic field produced by a straight wire, finite, infinite. But that also will not be applicable here. So you are left with only one approach. You have to consider the loop as a collection of elements. See why I'm explaining all this, it's obvious. But when you see a new situation also, this is how you are supposed to think. Can we consider the system, that new system that is given to you, can it be considered as a collection of systems whose results we already know? If not, you have to go to the basic method of taking it as a collection of elements. Okay, let's visualize one current element on this loop now. Let's say this one. The direction of the current element must be along the direction of flow of current. You cannot reverse that. It's a rule. Okay, let's say the current element is ideal as usual. Now, the approach we are taking is Biot-Savart law. In Biot-Savart law, we know dB is equal to, like from Biot-Savart law, it is mu naught I by 4 pi dl cross r divided by r cube. So ideal you considered, that's fine. You still have to consider the r vector. Can one of you quickly tell me from where to where r vector is to be drawn?
Ideal to P.
From?
Ideal to P.
From ideal to P, from the current element to the position where you want the magnetic field, correct? So this will be the r vector now. Okay, you'll have to visualize this in 3 dimensions, slightly difficult to show on screen. Okay, r vector is visualized. Can any of you tell me the magnitude of r vector?
Root of radius square plus x square.
It will be root of capital R square plus x square. Because as I said, you have to visualize this in 3D. If you imagine joining different current elements to that point P, all these lines, what do they form? All these lines together, what do they form? They form a cone. Okay, the ring is like the base of the cone. That loop, circular loop, is like the base of the cone, and that point P is that apex or vertex, whatever you call it. Fine. Any line you draw from the edge of the base to that point P, it will have the same length. Okay, on screen in 2D, these yellow lines may appear to be of different lengths, but in 3D, they are all of the same length. Okay, I hope you all are able to visualize that. If any of you has any confusion in that, ask. Okay. It's like connecting points on the edge of the base to that vertex of the cone. Okay, I'll try to show you another diagram also. Fine. right? So any of these r vectors, from any element you take the r vector, its magnitude is going to be square root of capital R square plus x square. Why will it be like that? That distance x you can visualize. Now visualize the radius r. For that point dl, this is radius r, you can say. Now this is perpendicular. The axis of the loop is perpendicular to the radius anyway. So this becomes a right angle triangle, and small r is the hypotenuse there. So it becomes root of r square plus x square. In fact, if we take this last element, it will be easy to visualize. Suppose you consider this as dl, ideal. From there, if you draw the r vector, see, some of you may be very comfortable with this. Some of you may be finding it a little difficult to visualize. That's why I'm explaining a little slow. So this is small r for that element, for that pink ideal that I have taken at the lower end of the loop. That vector is r vector, and this angle is 90 degrees. For every element, it will be the same. Okay. Fine. So we got the magnitude of r. The other thing we need to know is the angle between dl vector and r vector, because we have to evaluate this cross product, dl cross r. We need the angle between dl vector and r vector. Can any of you tell me the angle between them?
90.
How much did you say?
Pi by 2.
Okay, pi by 2, 90 degrees. Fine. So that is correct only. Any element, like you join any element to that vertex of the cone, the angle will be 90 degrees. Just a moment. Okay, the situation is somewhat like this actually. This is the circular loop whose magnetic field we want to find out. You can think of it as the base of the cone, and the point P is here. Okay. Anyway, so this angle between any element and the corresponding r vector will be 90 degrees. Fine. So we can now write the magnitude of the magnetic field produced by one of the elements. dB will be mu naught I. All the elements have the same current by 4 pi I. Okay, there we already considered I. dl cross r, I'll write it as dl r sine theta, where theta is the angle between dl vector and r vector, divided by r cube. R gets cancelled, we'll be left with r square. Theta is 90 degrees, so sine theta becomes 1. Therefore, the magnetic field produced by one element would be mu naught I dl divided by 4 pi r square, small r square. We'll convert that into capital R and x terms later. Okay. Now we got the field produced by one element, but that is not what we are looking for. We want the field produced by the entire circle of current at that point P. How to do that? We'll have to integrate. Okay, integrate fields produced by small elements, you'll get the net field. Tell me, to get the net field now, can we directly write it is integral of mu naught I dl by 4 pi r square? Can we directly integrate this dB magnitude?
No, sir.
Yes, why not?
Sir, here because of symmetry, like the component sine theta will get cancelled, right?
Components. Okay, why do we have to take components?
Because
Okay.
magnetic field is a vector, right? So
Ha. vector also, but see in the previous cases, like this centroid, this 2 wires case, we didn't take components, we directly added the fields. How was it valid to directly add? Anyone?
Same direction, sir.
If vectors are in the same direction, you can simply add their magnitudes. That itself will be the magnitude of the resultant. But if vectors are in different directions and you want to add them or integrate them, you will first have to split them into components and integrate the components separately. Okay, so let us visualize the direction of magnetic field produced by each element here. Now, one element I have taken in green. Visualize placing your right hand thumb along that green vector and the fingers along this position vector. If you do that, okay, it's a little difficult to show, but I'll try. Hope you all are able to see. Okay, wait. So, okay, I'm seeing my own face. We'll stop the video. No. Okay, it is difficult. Leave it. Just a moment. Are you all able to see the screen?
Yes, sir.
Okay. Yeah, so imagine placing your thumb along that vector. Now see, that vector is not the DL vector, ideal vector is not in the plane of the screen. In 2D diagram, it appears like that, but you have to imagine it like a ring, okay? So your thumb will not be placed parallel to the screen. You'll have to incline your thumb like this, okay, into the screen a little bit, because in that element, green element, current is going into the screen, okay? So incline your thumb a little bit and you point your right hand fingers this way towards the point P. So thumb is along the element, fingers are along the vector R. Then the cross product will be this way, okay, like in a direction perpendicular to your palm. So in this diagram, the cross product would be, I mean, the magnetic field would be somewhat in this direction. Okay, I'll draw that also in green because it was produced by that element. So this is the magnetic field dB produced by that green element. Okay. Next, the pink one, if you see, in the pink one, the current is coming out of your screen. Okay. So you'll have to take the thumb this way out of your screen as seen by you. Thumb is this way, and you'll have to place the fingers like this towards the point P. Then if you do that, the magnetic field will be directed upwards like this. Not exactly upwards, it will be tilted, because your fingers are also tilted. They are not horizontal, they are at an angle like this. And the magnetic field would be like this. So magnetic field produced by that last element is in this direction, dB. Fine. So if you visualize the magnetic fields produced by all the different elements, you will see them forming a cone like this. Again, these vectors also you have to imagine in 3D. Some of them point out of your screen, some of them point into your screen. Okay, I should not show it like that. There will be some fields like this. Right? So you'll get a bunch of, not bunch, you'll get infinite number of dB vectors like that. Is this point clear to all of you, that magnetic field visualization? If you have any questions, you can ask. Okay. Now see, the dB magnitude we got was this. For every element, R is the same. So R is a constant here. From every element to that point P, the distance R is the same. And DL is DL, let it be. Current I is same in all the elements. So the magnitude dB of the magnetic field produced by all the elements is the same. So this bunch of vectors that you see here, they all have equal magnitude. Okay, but they are pointed in different directions, as you can see. What do you think will be the direction of their resultant? Or is it difficult to determine? There's a bunch of vectors of same magnitude distributed like a cone. Okay, I'll show the diagram here. What do you think will be the direction of resultant of that bunch of vectors?
Radially inverse.
Radially inward. So on this, in this case, it will be towards left. Because for all those vectors, the x component is towards left itself. Some of them have positive y components, some have negative y components, they'll cancel. Some of them have positive z components, some have negative z components, they'll also cancel. But x components for all the vectors are to the left. So the net magnetic field there will be to the left. Okay. So one factor is that they are all of the same magnitude. And another factor is that they all make the same angle with the axis of the cone. So from symmetry, you can say that the resultant will be along this direction, along the inward direction. Okay. Why is this important? Because the individual fields dB were in different directions. We are looking for the net field. Okay. And if dBs are in different directions, we have to integrate components. We know that. Once you visualize the net field, you will know which component matters and which component doesn't matter. So in this case, if you want the net magnetic field, you will only have to integrate the x component of every small magnetic field. You don't need to integrate y components and z components. That is the advantage if you integrate the net, if you visualize the net field. Okay, net field is only in the x direction, so take only the x components and integrate. Okay, to take the x component, let us visualize only one field clearly. Again, this is a three-dimensional diagram. It is slightly difficult to show properly on screen. Let's not consider this element. Let's take that lowermost element itself. I'll remove the other arrows. Right. So that lowermost element is producing a magnetic field dB as shown in the diagram. We have to find out, we need its x component, right? So we have to find out what angle it makes with the x-axis. Let's call this angle as alpha. If that angle is alpha, this angle will be 90 degree minus alpha. Why? Because dB is along the cross product of IDL and R. Okay, not equal to, but it's parallel to IDL cross R. And we know cross product of two vectors is perpendicular to both the vectors. Okay, so the dB vector is perpendicular to the R vector. So angle between them totally has to be 90. If that upper side angle is alpha, lower side will be 90 minus alpha. And you can see a right angle triangle here. If that angle is 90 minus alpha, then this angle becomes alpha. In fact, I don't think you need that. But you can say that that angle will be alpha. Okay. To take dB's x component, which is what we need to integrate, you need dB cos alpha. Let us use this right angle triangle to get cos alpha. We'll make use of this right angle triangle to get cos alpha. Now in this triangle, you can see alpha. Alpha is at the lower side like this, lower corner. For that, the adjacent side is the radius r and the hypotenuse is the distance small r. So cos alpha becomes capital R divided by small r. That's all. We can now write dB is x component and we can even integrate it. Okay. Therefore, net magnetic field, which is integral of x component of dB, becomes integral of how much was dB? Mu naught I dl by 4 pi r square. And you have to take its x component, so you'll have to multiply with cos alpha, which is capital R by small r. That's all. So finally, we have gotten somewhere. Let's put all the constants aside now. The current is the same in every element. Capital R is the radius of the circular loop, which is constant, which is a fixed value, 4 pi. Small r is the distance from any element to the point P, which is also same. Okay, so small r cube. Only thing you need to integrate is dl. Let us look at the diagram. dl is nothing but the length of the element, right? So if you integrate the lengths of all the elements, how much does it become? Anyone?
2 pi r.
It becomes a circumference of that circular loop. You are not integrating element vectors. Okay, the dl that you see in the integral here is just the magnitude of that element's length. Direction doesn't matter. So if you add all those element lengths, okay, it becomes the total circumference of that circular loop, which is 2 pi capital R. So integral dl becomes 2 pi capital R. Therefore, the net magnetic field on the axis of a circular current carrying loop is mu naught. 2 pi and 4 pi will cancel. 1, 2 will be left in the denominator. Mu naught I r square by 2 small r cube. Okay, let's keep it as small r cube itself for now. Fine, but smaller is that slant distance. Nobody will give you that distance in the question. They'll give you the perpendicular distance x. So in terms of x, if you write this same result becomes mu naught I r square divided by 2. What was small r? Small r was root of r square plus x square whole power 3. You can write it as r square plus x square whole power 3 by 2. Okay, that's the magnetic field on the axis of a circular current carrying loop. This derivation is there in NCERT also, so this is important even for your board exams. Okay, and the result is important for entrance exams. Okay, now you can imagine, like you can visualize how we considered the current in this loop and all. Out of the screen, current was flowing upwards. Behind the screen, it was flowing downwards, okay, as seen by you. Now, on this side of the loop, we find that the field will be directed towards the center of the loop, that is to the left. If you take a point on the other side of the loop, somewhere here, can one of you tell me what is the expected direction of magnetic field at that point? Is it to the left or to the right?
Right.
Okay, I got one answer as right. We'll see. Others also give your answer. I want the direction of magnetic field at this point Q due to this circular current carrying loop. Okay. To visualize this, I think the other right hand rule, the like curling your fingers thing will be easier. Place your right hand fingers along DL vector, that green vector. So if you place your right hand fingers along that vector, you'll be pointing your fingers into the screen. Okay. And as I said, the palm should be towards the position Q and curl them. You will see that this green element will produce a magnetic field at that point in this direction. The dB will be this way. The other dBs will be like this. They'll all form a cone like this now. And the resultant will be towards left itself. It will not be towards right. It will be towards left. Sashank, are you able to visualize?
Yes.
It will be towards left. So everywhere along the axis, the field will have the same direction. Right? And we are talking about a magnetic field. This magnetic field is produced by a circular loop of current, right? On one side, the field is directed into the loop. Okay, like on the right side, the field is directed into the loop. On the other side, it is directed out of the loop. This is what we call a magnetic dipole. The side on which the field is entering into the loop, that becomes the south pole of the magnet. And the side where the field is going out of the loop, that becomes the north pole of the magnet. So this effectively behaves like a magnet. Current carrying loops behave as magnets. This is the principle behind the working of electromagnets. Okay, you can use electricity to produce magnetic fields, to make magnets, or to produce magnetism. And this is how it is done. Okay. And there's a south, there's a north, so it's a magnetic dipole basically. You can take a bar magnet near this, you will see that it will get attracted to it or repelled by it. Okay, they will exert force on each other. So you can prove that this actually produces magnetism. And observe the field formula also that we derived. On the axis, we got this formula, that's fine. Now, if the distance x is much greater than the radius of the loop, okay, that means we take a point far away from the current carrying loop. Tell me, what adjustment can we make in this formula if x is much greater than r?
R square can be neglected.
If x is much greater than r, x square plus r square will approximately be equal to x square itself. R square in the denominator can be neglected. Okay. If you neglect the r square in the denominator, then you will be left with x square whole power 3 by 2, which is x cube. The magnetic field formula on the axis changes to mu naught I r square by 2x cube. This is what is interesting. Can any of you tell me the formula for electric field on the axis of an electric dipole? Suppose dipole moment is P, electric dipole moment. At a distance x on its axis, axial line, what is the formula for electric field produced by an electric dipole? Distance from the
2
center of the
kp by
dipole.
r cube.
2kp by
X
x
cube.
cube, r cube or x cube. Fine. So it is inversely proportional to cube of the distance. Here also we see the same. The magnetic field on the axis of this magnetic dipole is inversely proportional to x cube. That is what makes it interesting. Magnetic dipoles are analogous to electric dipoles. Okay, the electric field produced by an electric dipole and the magnetic field produced by a magnetic dipole, they have a lot of similarities between them. Okay, we'll discuss this point in detail in the next class. Some more questions also we will solve based on fields produced by straight wires, arcs and all. But do this derivation once on your own. Okay, even that straight wire derivation that we did in the last class. Okay, we considered one element, we integrated, small adjustment we had to make. We had to convert different variables, all of them into theta, d theta and all. Okay, do that derivation once on your own and then this one. Okay, fine. Thank you all. If you have any questions, you can ask. I'm closing the session here.
So
Yes.
what if we reverse the direction of current in this last case?
If you reverse the direction of current, all the ideal vectors directions will get reversed, right? Then
So
all
the
the
north and south will change.
all the dB vectors will get reversed. Then the field will be directed the other way. This side will become south, the other side will become north. Yes. Okay. Some of you may have made electromagnets also. Like you take a bolt, okay, made of iron, wind a copper wire around it, connect the wire to a battery. Current will flow in that wire, and that winding is like a collection of circular loops. Each loop produces a magnetic field, and the collection of loops produces an even stronger magnetic field. And the bolt will be able to attract nails or other objects made of iron. Have any of you done that experiment in your childhood, like 6th class, 8th class?
Yes, sir.
Anyway, you can easily find it on YouTube also. Just take a look at that. Just type electromagnet. Okay, you can find videos and photos. Okay. Right. Thank you all. I'm closing the session here. We'll solve questions based on wires and circular arcs in the next class, and also this magnetic dipole. Okay. We'll derive a general formula for magnetic dipole, how to write the field produced by a magnetic dipole. You can, like this formula that we derived now, we can extend this in general to any loop of current, having multiple turns also. Okay. All those things we'll discuss in the next class. Okay.